Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we'll go through everything you need to know for the upcoming test. So the test covers statistics, probability, and equations. So let's start with statistics. So firstly, in statistics, we will look at how to display data. So I've written down the hair color of some students in a class. What we're going to do is display this information in both a dot plot and a column graph. So what we might do to make it easy on ourselves is draw up a frequency table. So that's just where we write how many of each category there is. So here, the data is in categories: blonde, brown, black, or red hair. So for each of these, we just count how many there are. So there are 6 people with blonde hair. It might be easiest if we now cross those out. So then the number of people with black hair, again, it might be easy if we cross them out. We have 1, 2, 3. And then we'll do the same for brown and red. So after we've filled in our frequency table, we'll just quickly check that the number in our frequency table is the number of observations that we had. So usually in frequency tables, you see something like this. This means sum of frequency. It basically means the total. So 6 plus 3 plus 3 plus 5 is 17. So we just might quickly check that up here there are 17 descriptions of hair, and there are, so we know we've done something right. So now that we've got this frequency table, it's going to be really easy to draw a column graph and a dot plot. So to draw a column graph, we first need 2 axes, 2 lines at right angles. So the vertical axis, the line going up or down, is always frequency. This is how many times the thing occurred. So on the horizontal axis, we're going to put the categories. So we need to label it. In this case, we're going to label it with hair color. That will go along the horizontal axis. So for frequency, the highest frequency here was 6, so we're going to go up to 6. So what will happen is each category, in this case, each hair color will get its own bar. So we'll start with blonde. So there were 6 people with blonde hair. So we draw a column or a bar for blonde up to frequency of 6. And now we'll do the same for black. It will get its own bar, but it will only go up to 3 because there are only 3 people with black hair. And then we do the same for brown and red. So now our column graph is complete, each category getting its own bar, and how high the bar goes is determined by how many times the thing occurred. So we also need to be able to get a column graph like this and interpret it. So we can see from the column graph, for example, that the fraction of people with blonde hair was 6 out of 17 in total. So blonde was the most common hair color and black and red were the least common. So displaying this information in a column graph gives us a very quick way to see what was the most common hair color and what was the least common. All right, now we're going to rub this out and I'm going to put the same information in a dot and plot. So please pause and copy this down if you need. So for a dot plot, we're only going to have one axis along here, and it's going to be the different categories. So this is hair color. We again write the 4 categories. So now, instead of drawing a bar for each of these categories, what we're going to do is we're going to put dots. The number of dots we put above each category is how many times it occurred. It's frequency. So for blonde, it occurred 6 times. So we put 6 dots up like this. So this is very similar to a column graph, just replacing the columns with dots. So similarly for black, we're going to draw 3 dots because black happened 3 times. And then for brown, we draw 5 dots, and red, we draw 3 dots. And then our dot plot is done. How easy is that? The frequency table just made it a little easier to construct this dot plot. So this data here is called categorical data because we've arranged the data into categories: blonde, black, brown, and red. So we can't calculate the mean, median, mode, or anything like that because it's not numerical data. Numerical data is when the observations you collect are not a category like blonde or black, but rather the observations you collect are a number. So we're now going to look at an example involving numerical data. So please pause and copy down this example if you need. So let's say we have these 10 test scores on your screen. So this data is numerical because if I ask you your test score, you're going to give me a number. Now I could display this data in a dot plot or a column graph, histogram, but it wouldn't be very enlightening and it'd take me a long time to do. So the reason it would take a long time is look at the huge range of scores. They go from 59 to 100. We wouldn't want to label our axis 59, 60, 61, and so on all the way up to 100. That'd take forever. The reason this also wouldn't be enlightening is because 8 of the scores only occur once, and there's only one score that occurs twice. So if I were to draw columns, like they'd all be like 1. They'd all go up to a frequency of 1, and it wouldn't really help us. Instead, what we're going to do is we're going to display this in a stem and leaf plot. What we're doing is we're grouping the data in tens. All the scores in the 50s go together, all the scores in the 60s, the 70s. It's just a more convenient way to display the data. So this is how we set up a stem and leaf plot. So for our purposes, the stem is essentially the tens. So we're going from the 50s to the hundreds. So we put 5, 6, 7, 8, 9, 10. From the 50s to the 100. Now note, we put the 6 in even though there were no scores in the 60s. We don't skip them. So we have to make sure the data is in order from smallest to largest in order to be a valid stem and leaf plot. So in the leaves, we just put the units. So this score here, 59, it's 5 tens and 9 units. So to represent that score, I just put a 9 in the leaf. So there were no scores in the 60s, so we're just going to leave the leaf for the 60s blank. So now let's go to the leaf for the 70s. Well, there are a few scores in the 70s, 72, 74, and 77. So I need to put them in order from smallest to largest. Smallest closest to the stem. So I put 2, 4, and 7. And it's understood this score means 72, this means 74, and this means 77. So then I can do the same for the 80s. I've got 3 scores again in the 80s. So I write the smallest one first. Now 88 occurred twice, so I need to write it twice. And then if I go to the 90s, there were 2 scores, and the last score, 100, has 10 tens and no units. So once again, I should check that the number of scores in my display is equal to the number of scores I started with. So both have 10, I know I've done something right. So this is how you display data in a stem and leaf plot. It's pretty simple. Now, because this data is numerical, I can calculate statistics, not just display them. So I'm going to calculate the mean, median, mode, and range. So we'll start off with the mode. So the mode of the data is just the most common. That's the easiest to find. So here, 88 is the mode, because it's the score that occurred most, the only score that occurred twice. So I just want you to be aware, when you have data, there can be more than one mode, and if no scores are repeated, then there is no mode. All right, let's now go through the median. So the median is the middle point of the data. So when there are an odd number of scores, there's one middle score. Here, however, there are an even number of scores. There were 10 scores up here. So what that means is there will be 2 middle scores, and we need to take the average of them. So one thing that's really important is when you're finding the median, the scores must be in order. So what I mean by that, see the data written up here in black. I can't find the middle score when it's written like this because it's not in order. I need to find the middle score when the data is written in order. And that's one good thing about the stem and leaf plot. It helped me put the data in order. So there are 10 scores. It can be tricky for you to think which of these scores are the middle scores. So a technique that you might like is to cross out the scores like this. What we'll do is we'll cross out the top score and the bottom score. Then we'll cross out the second bottom and second top, third bottom and third top. So we're doing one at the bottom, one at the top. Then we'll calculate the next bottom score, we'll cross that out, and then we'll cross out the next top score. And then we stop when we get to the middle, where there's no more to cross out. So here, the two middle scores are 86 and 88. So the median, when you have two middle scores, you need to find halfway between them. So I add them up and divide by 2. So the median is 87. So the median is here. You can see that before this blue line, there are 5 scores. So there are 5 scores less than the median. And there are also 5 scores above the median. So that's the point of the median being the middle score. Remember, odd number of scores, there's one middle score that's the median. Even number of scores, there's 2 middle scores, and you take their average. And if you've got a lot of scores, it's helpful to put them in order and then cross out the bottom one, cross out the top one, and then keep doing that until you get to the middle. All right, let's now calculate the mean. So the mean, which is commonly called the average, it's just the sum of all the scores divided by n, which is the number of scores. So in this case, there are 10 scores. We're going to add them all up and divide by 10. So if I add up all the scores, I get 828. So the mean is 828 divided by 10. Now in this case, I don't get a whole number. It's 82.8, but it doesn't matter. The mean doesn't have to be a whole number. So all of these measures here, the mean, median, and mode, they're supposed to tell us about the center of the data. They're supposed to summarize the data, give us an indication of what is a typical score. So there's another measure we went through, the range. It doesn't tell us about the center of the data. It tells us how spread out it is. How big is the difference between the top and the bottom score? So the range is just the highest score minus the lowest. Now, people, when they're asked for the range, they often write things like 59 to 100. No, when you're asked for the range, your answer needs to be one number. So it will be the highest score minus the lowest score, which is equal to 41. The range is 41. So again, range is just one number. All right, that's all for statistics. Let's now move on to probability. So let's now look at probabilities. Let's say I roll a normal 6-sided die. You've seen them a million times. So if I'm asked for the sample space, this is just a list of all the possible outcomes. So you need to put it in these brackets here, these squiggly brackets, because that in maths means a set. So all I'm going to do is write the possible outcomes. So I could get a 1, 2, 3, 4, 5, or 6, okay? So whenever you're asked the sample space, just list the possible outcomes. So now we've got to actually look at assigning probabilities to an event. So when we're talking about probability, what we do is we give an event a number between 0 and 1 to indicate how likely it is to occur. So if it has a probability of 1, it's certain, a probability of 0, it's impossible. So if the probability is close to 0, we say it's unlikely. If the probability is close to 1, we say it's likely. And of course, if it's smack bang in the middle, if its probability is 0.5 or a half or 50%, then it has an even chance of occurring. So when you are asked for the probability of an event, you must give a number between and including 0 and 1. Doesn't matter whether you write it as a decimal, fraction, or percentage, but it has to be a number between 0 and 1, and that number indicates how likely it is to occur. So how do you actually calculate the probability of an event? Well, we use this formula here. So PE means probability of an event. NE, the number of ways it can occur. NS is the total number of outcomes, or the total number of outcomes in the sample space. So that's how we figure out the probability. So let's make sure we get the notation right. So if I write something like this, probability of 6 is what it means. So there is 1 6 on the die out of 6 outcomes in total. So if I say probability of 6, you can't say unlikely. You need to give me a number between 0 and 1. It's 1 over 6. There's 1 6 on the die out of 6 outcomes in total. Sometimes probability is written with PR as well, and that's fine too. So if I ask for the probability of an even number, So it can occur three ways. I can get a 2, a 4, or a 6. So the number of ways I can get an even number is 3. Once again, the total number of outcomes is 6. So the probability of getting an even number is 3 over 6, or a half, 50%, 0.5, doesn't matter which way you write it. So let's say the probability that I get a prime number. So let's count the number of ways it can happen. So we've got 2, 3, or 5. They're the prime numbers. So there's 3 ways that I can get a prime number out of 6 outcomes in total. So once again, that is half. So let's find the probability that I roll a multiple of 3. So again, we just count how many ways can I get that? How many multiples of 3 are there? Well, we have 3 or 6. So there are 2 ways that can occur this time out of 6 outcomes in total. So it's just 2 over 6 or 1/3. So just looking at that last one, 1/3. So that would be like down here on the number line. So that's unlikely that that would occur. It's unlikely you'd get a multiple of 3. It's more likely you don't get a multiple of 3. So the probability you don't get a multiple of 3, well, I can actually get that 1, 2, 3, 4 ways out of 6. So 4 out of 6 is 2/3. 2/3 is up around here. So it's likely that you will not get a multiple of 3. All right, the last example I'll do, what's the probability you roll a 4 or 5? That doesn't mean you choose one. It means how many ways can I get a 4 or 5? Well, there's 1 way I can get a 4 or I can get a 5. There's 2 ways it can happen out of 6. So the probability of this one is 2 out of 6 or 1/3. So what we're calculating in each of these examples is theoretical probability. What we're calculating is the proportion of times something should happen, or the proportion of times I expect something to happen. So when I calculated the probability of a 6, I'm saying that I expect that if I roll a die heaps of times, I will roll a 6 1/6 of the time. I expect if I roll a die heaps of times, I'll get an even number half the time. So this leads us into expectation, which I'll go through on the next slide. Please pause and copy down if you need. The number of times that I expect something to happen is its probability times the number of trials. So that makes sense given what I just said. So let's say I roll a die 150 times. So I just figured out that the probability of rolling a 6 is 1/6. I expect that if I roll a die 150 times, 1/6 of the time I'll get a 6. So the number of times I would get a 6, the number of 6s I expect is 1/6 times 150. 1/6 of 150, which is 25. I figured out the probability that I roll a prime number is a half. So if I roll a die 150 times, I expect that I will roll a prime number half of those times. I expect I'll roll a prime number half of the 150 times. Half of 150 is 75. So that's how you figure out the expected number of times something happens. It's the theoretical probability times the number of trials. But of course, if I roll a die heaps of times, I might not get a 6 exactly 1/6 of the time. I might not get a prime number exactly half of the time. And that's where experimental probability comes in. And we'll go through that on the next slide. So when we were using that formula before, in fact, on this video, all the probabilities I've calculated to this point have been theoretical probabilities. We've calculated the fraction or proportion of times we expect something to happen. But of course, what we expect to happen and what actually happens are not always the same. So experimental probability is the fraction or proportion of times something actually happens. So this is very important because sometimes we can't calculate the theoretical probability. How are we going to calculate, say, the probability that you're sick tomorrow? That's actually really hard. There's no formula that can really do that. But instead, what we could do is we could look at the proportion of times that you've been sick this year, and that can give us an indication. So if you've been sick, 3 out of 100 days, the experimental probability you're sick is 3 over 100. So let's go back to rolling a die. So let's say I rolled a die and I rolled a 5, then a 4, and so on. So I rolled a die a number of times, and these were my results. So we know, for example, the theoretical probability of rolling a 5 is 1 over 6. So in this case, the experimental probability of rolling a 5, I rolled it once, and there were 8 trials in total. I rolled the die 8 times. So the experimental probability of getting a 5 here was 1/8. So again, just because the theoretical probability is a 6th, I expect to roll a 5 1/6 of the time. That doesn't mean I always will roll it 1/6 of the time. The experimental probability of rolling a 2, I rolled it 2 times out of 8. So it's 2 over 8 or 1/4. So the experimental probability of rolling an even number. So I rolled an even number 1, 2, 3, 4, 5 times out of 8 trials. So it's just 5 over 8. So remember, we calculated the theoretical probability before. The theoretical probability of rolling an even number was 3 over 6, or a half. We expect that if we roll a die heaps of times, we'll roll an even number half the time and an odd number half the time. But that doesn't always happen. Sometimes we roll a die heaps of times and we get even more than half the time. And that's what happened here. So the experimental probability is 5 over 8. It's different to the theoretical probability of a half. The theoretical probability and experimental probability are not necessarily equal. All right, let's move on to the final topic here of equations. So an equation is an expression with an equal sign, something like 4x equals 28. So what we have is an unknown number x, had some operations performed to it, we've got an answer. We want to figure out what the original number was. We're trying to solve this. We're trying to find what number can I substitute for x to make this a true statement. So most people can probably do this off the top of their head. The solution is x equals 7, because 4 times 7 equals 28 is a true statement. The solution's not x equals 10, because 4 times 10 does not equal 28. So there's one and only one solution to the equations we're going through. Now, if you couldn't figure it out off the top of your head, that's okay. What we do is we undo what's already been done to x. So in this equation, x had been multiplied by 4. So the thing that undoes multiplying by 4 is dividing by 4. So if I didn't know the answer off the top of my head, that's okay. I could just go x equals 28 divided by 4, which is equal to 7. So when you're writing a solution, it must be x equals something or a equals something or whatever. So that was a one-step equation. There was only one operation that had been done to x. So let's look at some where there are more than one operation done to x. So let's solve the equation 2x plus 1 equals 7. So I taught two methods, the balance method and the flowchart method. You can use either. I'm going to do this one using the flowchart method. So the flowchart method is you start with x and you tell the story of what happened to it. So I took x and then I times by 2, then I added 1 and ended up with the answer of 7. That's what's happened here. X has been multiplied by 2, then 1 has been added, and then I got 7. So to solve the equation, I start with my answer 7 and go the other way. So instead of adding 1, I subtract 1. So 7 minus 1 is 6. And then instead of timesing by 2, I divide by 2. So 6 divided by 2 is 3. So the solution here is x equals 3. If I substitute x for 3 here, I get a true statement. So when we're undoing what's been done to x, we need to undo in the opposite order to BODMAS. So when I'm undoing, I undid this addition first and then I undid the multiplication. So let's look at an equation like this. So 4 outside of x minus 8 equals 24. So remember, the brackets change the order of operation. So what I've done to x is I've subtracted 8 first, then times by 4 to get my answer 24. I'm going to solve this one using the other one, the balance method. So the first thing I'm going to do is I'm going to divide by 4, because that will undo timesing by 4. So the premise behind the balance method, what you do to one side, you must do to the other. So if I divide the left-hand side by 4, I must also divide the right-hand side by 4. So I'm left with x minus 8 equals 24 divided by 4 is 6. Now I need to undo subtracting 8 by adding 8 to both sides. And the answer I get is x equals 14. If I substitute x equals 14 into this equation here, I get a true statement. All right, let's look at some involving fractions. So let's look at these two equations that have the same numbers and the same operations in them, but they'll actually have different answers. So the reason they'll have different answers is the order of operations is different. So if you do the wrong order of operations, you will get the wrong answer. So in this one here, I've added 2 first, then divided by 3. Here I've divided by 3, then added 2. So we're going to solve these like normal. We're going to undo what's happened to x. So in the left-hand one, I'll use the flowchart method. So what we did was we took x, added 2, then divided by 3 to get our answer of 7. So to solve it, I start at 7. Instead of dividing by 3, I'm going to times each side by 3. So 7 times 3 is 21. Then instead of adding 2, I subtract 2. 21 minus 2 gives me 19. So x equals 19 is the solution to this equation. So let's do the right-hand one using the balance method. I'm going to get a different answer because the order of operations is different. So in this one, because I divided 3, then added 2, my first step is I need to subtract 2. And if I subtract 2 from the left-hand side, I must subtract 2 from the right-hand side. So I get x over 3, the 2's cancel each other out, equals 7 minus 2, which is 5. So now I need to undo dividing by 3. So this fraction means divide. So I undo dividing by 3 by multiplying each side by 3. 3's cancel out. I'm left with x equals 5 times 3, which is 15. So I got a different solution because the order of operations was different. So just make sure you're clear on what has been done to x. What has been done first, what has been done last. All right, let's do one that's a little more challenging. So this equation down the bottom is more challenging because the x is in more than one spot. So before I can start solving using the balance method or the flowchart method, I need to get x to one spot. My only choice is to expand the brackets. Remember, I distribute the 3 to the 2x and the 3 to the minus 1. So I leave the 4x alone. 3 times 2x, 3 times negative 1. Now I need to get x to one spot by collecting like terms. So 4x plus 6x is 10x. So I've got 10x minus 3 equals 37. So I'm going to solve this using the balance method. I add 3 to both sides to undo subtracting 3. So I get 10x is equal to 40. And now I've got to undo timesing by 10 by dividing each side by 10. And the answer I get, x equals 4. How easy is that? All right, let's now move on to rules and formula. One use of equations is to find the unknown variable in a formula. So y equals 3x minus 7 is a formula. It's an equation because it has an equal sign and it has 2 variables, 2 pronumerals. Y is the subject. So this is a rule or formula. So what we're going to do is we're going to use what we know about equations to find what's the x value when y is minus 11. So all we need to do for this is take our equation y equals 3x minus 7, and I'm going to change y into minus 11. So now I can just solve like I solved all the other equations. To get x by itself, I'm going to add 7 to both sides because add 7 undoes subtracting 7. So if I add 7 to the right-hand side, I must also add it to the left-hand side. So I get minus 4 equals 3x. and then I'm going to divide each side by 3, and I get minus 4 over 3 equals x. So I just want you to be aware that the answer you get for equations is not always a whole number. So 4 over 3 is not a whole number, and it's not always positive. It can be negative as well. Don't just assume you've done something wrong. So that's all for rules and formula. Now the very final thing we're going to do is go through worded problems with equations. So now we're going to go through 2 worded problems using equations. One of them's quite easy, one of them is quite hard. Whether it's easy or hard, we're going to follow the same process. So when you're solving worded problems using equations, you always start by defining a variable. So what that means is let x equal whatever you're trying to find. So after you've defined the variable, you need to form an equation. You need to take the worded information and rewrite it using only mathematical symbols as an equation. And then the third step, you just solve the equation as we've done a million times. So let's look at the first one. 4 is subtracted from a number, the result is doubled, the answer I get is 12. What was the original number? So we're trying to find the original number. So we let x be what we're trying to find. Let x equal the original number. So now what we're going to do is rewrite the information using only mathematical symbols. So 4 is subtracted from the original number, which is x. So 4 is subtracted from original number, and then we double our answer and get 12. Now that we've got the equation, we've kind of done all the hard work. We solve this as normal. So I'm going to divide each side by 2 and then add 4 to each side. So the original number was 10. If you subtract 4 from 10, you get 6. Double it, you get 12. So a worded question needs a worded answer. So you just say something like, therefore, the original number, because that's what we were trying to find, the original number is 10, and you're done. So let's look at the second one. 1/4 of a class of students has blue eyes. 3 blue-eyed students then leave the class. There are now 4 students with blue eyes, and we want to find how many students were in the class originally. We're going to follow the same process. So step 1, we're going to let x equal the thing we're trying to find, which is the number of students in the class originally. So then we rewrite this worded information here using only mathematical symbols. So 1/4 of the number of students in the class has blue eyes. Then we took away 3 students with blue eyes, and now there are 4 students with blue eyes. So now we've got the equation, all the hard work is done. We're just going to solve this the exact same way we've solved all the other equations. So first thing I'm going to do is add 3 to both sides, and I get 1/4 x equals 7. So we have 1/4 times x. If no operation's written, it's times. So the way we undo timesing by 1/4 is divide each side by 1/4. So in the test, make sure you use your calculator for this, just to double check you've got it right. So 7 divided by 1/4 is actually 28. So I have found that there were 28 students originally in the class. So that means that 7 of them, 1/4 of them, had blue eyes, then 3 students with blue eyes left, so now there are only 4 with blue eyes. Okay, so I know that this is a hard one, but let's always follow this process for worded problems involving equations. Let x equal the thing you're trying to find, turn the worded information into an equation, and then solve it as normal. All right, thanks so much for watching. First 3 people in my class say Caramello Koala and reference this video. You can have one. Best of luck studying for the test. You're a superstar. You will ace it. This has been the luckiest maths teacher in the world. Have a great day.